All right, let's graph another rational function. I've got my coordinate plane here. I've got my rational function up here. I need to identify several of these qualities that I can then put on the coordinate plane and draw my curve. So what's the first thing we normally do? First thing we normally do is if it's factorable, we factor the numerator and we factor the denominator. Now notice here, this denominator is a linear denominator, and it doesn't have any common factors in it, so it's factored. It's as far as we can go. But that numerator, we can factor that thing. Two numbers that multiply to negative 15 but add up to positive 2 would be positive 5 and negative 3. So this is going to be x plus 5 times x minus 3 all over x minus 2. Now what do you notice here? You notice something interesting? No matching factors in the numerator and the denominator, which means that we can't cancel anything. That also means that there are no holes. No holes, okay, at all. Okay. Well, then let's see if we can identify a y-intercept, shall we? Let's put zeros in. If we put a 0 in here for x, and put a 0 in here for x, we get 0 plus 0 minus 15. Put a 0 in here, we get 0 minus 2. And so this is negative 15 over 0 minus 2 is negative 2. And negative 15 divided by negative 2, well, that's 15 over 2, which is also the same thing as positive 7.5. But I would put it as 15 over 2 and then find the point 7.5. So we're going to go 0, we'll put 0 and 15 over 2 is the y-intercept. So we're going to 7.5. 1, 2, 3, 4, 5, 6, 7. 7.5 is right here. There's our y-intercept. Okay, now we want to identify the x-intercepts if there's one or more. To identify the x-intercepts, we set the numerator equal to 0. So we're going to set x plus 5 times x minus 3 equal to 0. Well, this is already factored. If you're in factored form, what you do is you set each of the individual factors equal to 0 and solve. So we'll do x plus 5 equals 0. Actually, I don't need this parentheses. Let me do this here. X plus 5 is equal to 0, and then separately x minus 3 equals 0. Subtract 5 from both sides, and we get x equals negative 5. So one of our x-intercepts is at negative 5 and 0. So negative 5 and 0. Over here, we're going to add 3 to both sides, and we're going to get x equals 3. Okay, so that's positive 3 and 0. So we've got our x-intercepts. One of them is at negative 5 and 0. 1, 2, 3, 4, 5. So that's negative 5. And the other one's at positive 3 and 0. 1, 2, 3 and 0. Put a dot there. There we go. So we've got our x-intercepts plotted. We've got our y-intercept plotted. Now let's see, are there any vertical asymptotes? Well, to find the vertical asymptotes, we set the denominator equal to 0. Denominator is x minus 2. Set that equal to 0. Add 2 to both sides, and we get x equals 2. So there is a vertical asymptote at x equals 2. So we're going to go over to our graph. We're going to go to positive 2. That's 1, 2. Right there, we are going to draw in a dashed vertical line. There we go. There's our vertical asymptote. All right. And now, horizontal asymptote or slant asymptote. The graph has a horizontal asymptote only if the numerator power and the denominator power are either equal or the denominator power is larger than the numerator power. Well, in this case, our denominator power is 1. Our numerator power is 2. That means the numerator power is larger, so there's not a horizontal asymptote for this graph. However, because the numerator power is 1 higher than the denominator power, that means that there is a slant asymptote. Okay? And so, here's how we're going to find the slant asymptote. To find the slant asymptote, we're going to use some kind of polynomial division. We're going to divide this into this, divide the denominator into the numerator. Now, because this is x minus 2, it's not a complicated, it's a linear, it's 1x to the first power, we can use synthetic division. So we're going to use synthetic division. We're going to put a positive 2 in the half box. Then we're going to do a 1, then a 2, then a negative 15. We're going to put a 0 here. 1 plus 0 is 1, times 2 is 2, plus 2 is 4. 4 times 2 is 8, minus 15 is negative 7, and that's the remainder. But remember, with a slant asymptote, we don't care about the remainder at all. We only care about the linear polynomial, the equation of the line, that results from the division. So, if we started out as x to the second power, this is x to the first power. So this is going to be x to the first. This is a positive 4 plus 4. And so we have y equals x plus 4. That is our slant asymptote. Y equals x plus 4. And what you have to understand here is a slant asymptote is a slanted line. It's a straight line. So it's going to take on the equation of a line, y equals mx plus b. And in this case, m is the coefficient of x. It's 1. The slope is 1, and the y-intercept is 4. So we're going to draw this line on the coordinate plane here. We're going to find the y-intercept positive 4, 1, 2, 3, 4. And then we know that it has a slope of 1. So that means it goes up 1 over 1, up 1 over 1, up 1 over 1, right? And here's what I'm going to do. I'm going to put this yardstick here, and I am going to draw this line, but I'm going to make it a dashed line. Remember, it's an asymptote, so I don't want to draw it as a solid line. I want to draw it as a dashed line. So, line this guy up there, line this guy up there. That looks about right. Try to hold it as steady as possible, and draw a dashed line. And there is my slant asymptote. Now watch this. Remember before we had a vertical asymptote and a horizontal asymptote, right? And so it gave us, here's a section, it gave us an above and a below. Here's another section, it gave us above and below, right? And we could only pick either above or below, and over here, either above or below, not both of them, right? Well, the slant asymptote works very similarly to the horizontal asymptote. If I have a vertical asymptote and a slant asymptote, I'm still dividing into this section and this section, but instead of having a horizontal asymptote, I have a slant asymptote, and I still have a below and above, and a below and above. And I can only pick one of them, either below or above. Either below or above. So here, look what we have here. Here's the vertical asymptote. Here's the slant asymptote. We can either select either below or above, and over here, either below or above. Now notice we already have some points in these sectors. On the left side here, we have this x-intercept, and we have this y-intercept, which means that the curve must be above the slant asymptote. So what I'm going to do is I'm going to go ahead and draw a curve in, and it's going to go through that point, then it's going to come down here and go through this point, and then it's going to kind of follow, I did that a little wrong, it's got to kind of follow the slant asymptote. So I don't want to make that curve too much. It's going to kind of follow the slant asymptote. Do you see that? Remember, the curves go along the asymptotes. So this one curves with this asymptote up here, and then down here it kind of curves at a slant, at a diagonal. Over here, are we above or below? Well, we have this x-intercept. So we know that the curve down here is going to follow the vertical asymptote, just like that. And then it's going to go kind of up here, and it's going to curve with the slant asymptote like that. Okay? And so that is the graph of this rational function. Instead of curving horizontally, it curves at an angle. It curves at a diagonal along the slant. Okay? And that is this rational function. We'll probably do one or two more, but I want you to see as many of these as you can so that you can get a feel for how to graph them. Okay?